Welcome to this brief screencast on searching and sorting arrays, chapter 7, section 4. So we're going to first talk about searching. So what is searching? Searching is trying to find something in an array. So a very simple algorithm for searching is to look at each item in turn, start at the beginning, look at that one. If it's the thing we want, then we found it, we're done, stop the search. If it's not the thing, we continue on. If you get all the way to the end of the array and you haven't found it, then the item's not in the array. So that's called a linear search, where we just start at the beginning, go all the way to end, and then, so the idea is that we're going to try to find n in an array of ints, where n is an int. So we do our for loop, standard processing for loop. We start at 0, we're going to go until length -1, and we step the way all the way through. So the if statement is to check. So if a at index is equal to n, we have found it, and we return the index indicating that we found the item at that index. If we get out of the for loop, because we've visited all the things in the array, we didn't find it, so therefore we return a -1 indicating that n was not in the array. Very simple, straightforward search. You start at the 0, go to length -1, checking each time, and you return if you find it, or you return -1 if you don't find it. Another way of searching is a binary search, which is a quicker search because we can divide the problem in half, but it requires a sorted array. So if we have an assorted array, we know that the first item is less than or equal to the second item, etc., etc., etc. If we look at the middle and compare that to our item, we can decide to search to the left half or search to the right half. And when we search to the left half or the right half, we've cut the problem in half, so we don't have to worry about the other half of the array. So we just keep doing that. We search to the left or we search to the right, and we just keep doing that until we've got to the point where the left and the right, the length of the array is 0, and there's nothing there, and it's not in there. So if it's in the middle and we find it, we return the index. If we get to the end when there's the thing is not there, we're done, and we return -1. So here's the code. So we still have our array A. We're looking for n. We keep track of the lowest index and the highest index, and we start with 0 and the array length -1. So we're searching the whole array. And then we have a while loop to say while we still are, so while the lowest index is less than or equal to the highest index, that means we still have things to check. We keep looping. So what do? We calculate the middle, which is lowest index plus highest index divided by 2. Check the item at the middle. If it is the item, we found it, we return the index middle where it is. Else, if the middle is greater than n, which means n must be in the left hand or lower side, we update the highest index to be middle -1. So now we're not considering anything higher than middle. And we go back to the loop and we recalculate a new middle, take our checks. But if the middle is not greater than n, then we want to say that n is bigger than middle, so we want to do the upper half. So we change the lower index to move to middle +1. The adding 1 and subtracting 1 guarantee that at some point lowest index and highest index will swap if it's not in the array. So that will end the while loop, and that will indicate that n is not in the array. So we keeping this, and we divide this in half, and then we divide it in half, and then we divide it in half until the two swap and it's not there, or we find the item. And this is a binary search, so we keep dividing the problem in half. It's much quicker than a linear search because we don't have to consider every item in the list. Another kind of list is an association list, very much like a dictionary where you have a word and a definition, or a name and a phone number, or a key and a value. That's a generic sense where you have a key and a value. So you look up the key and it has a value. So like you look up a word in a dictionary to get the definition. You look up a person's name to find out what their phone number is. And in our example, we're going to create a class phone entry, which has a name and a phone number. You can imagine having a dictionary entry with a word and a definition, all sorts of combinations for these names and or keys and values that we're going to do. So we have a phone directory that has an array of these phone entries, and then we have a data count to keep track of how many entries we have in our directory. So there's our thing. Our constructor is we create a new phone entry. We could use size 1, we could do size n, whatever, doesn't matter. We initialize it, and then if we want to find the index of something, we have a private method, find, that does a linear search that returns the index of the phone entry with that name. So we go from 0 to data length -1. If the data sub i's name is equal to the thing we're looking for, then we return the index, else we return -1. So that's our linear search that allows us to search all the entries for the phone entry with the given name. So now we could have another method that returns the person's phone number given their name. So we use find to find the index of the phone entry. If the position's equal to -1, that means it wasn't in the directory, so we return null. Else we return the entries at that position's phone number. So this is an easy way to return the phone number of a person given a name. And we do a linear search. If the item was in there, pause will be the index of the item, and we'll return the phone number. If pause is -1, then the name was not in the entries, there was no entry with that name, so we return null. To put an entry, we have a name, we have a number. So if the name is null, if the number is null, that's not legal because we have to have a name, we have to have a number. So we find the record with that given name. If I is greater than or equal to 0, that means it's there. So this person's name has a record. We just want to update their phone number. So we just update data sub i's phone number to be the number that we passed in. Else, we want to add this new phone entry to our data. So we check to see that our data array is not full. If it is full, data count equals to the length, that means we have a full. If that's so, we need to allocate more space, copy over the things, and assign it to the data, to the new copy. So we're going to use arrays copy to copy the contents of data into a new array that's twice as long as data, and then we assign that new array to data. So data now points to the new array that's a copy of the old data, but it got twice as much entry. And then we create a new phone entry given the name and number. We then insert that entry at the end, data count at the end, and then we increment data count. So we now have one more item in our thing, which is the new name and number phone entry. So that's a simple put and a get, so we can get the phone number for a given name. We can add a phone number and a phone entry by supplying the name and the number. If it's already in there, we update the number. If it's not, we enter a new one. So that's an example of an associated data or with an array, so we can actually think of the searching for names and getting their phone numbers. So the next thing we're going to talk about is doing sorts. So let's assume you have a sorted array and you want to add an item to the array and keep it sorted. So we want to insert this item, new item, into the array A that tells us there are so many items in A, number items in A, and we know that A is sorted. So in order to do that, we want to start at the right-hand end of the thing, the biggest side, because it's sorted from smallest to largest. So we create a variable loc, and we put it at the end. While loc is greater than 0, because we're going to go from the end to 0, so we're going to go from right to left, and the value at loc is greater than the item we're inserting, that means we need to shift that item because we need to create space for the new item in the right place. So if the thing at loc is greater than the item we're inserting, we move loc to loc plus 1, and we decrement loc. So we start at the rightmost one, then we go one over, and then we're going to check to see is that one greater than the new item. If it is, we shift it over, and we keep shifting, and that's creating a space by doing that shift. Once we're done with the while loop, we're in the right place, and we've created a gap. We say a at loc plus 1 equals new item. That inserts it into the right place. And then we need to increment the number of items in A, because we have increased the number of items in our array. So we can use this idea of inserting the thing in the right place in the array to sort an unsorted array of ints. Here's the example of inserting 15 into this already sorted. So we started the loc at the end. Loc is 4. Is 35 greater than 4? Yes. So we copy 35 over 1. We did the copy, and then we decrement loc. Now, is 17 greater than 15? Yes. So we copy it, and we decrement loc. Is 13 greater than 15? No. So we've got our position. We're in the space. We've got the gap. So we insert new item into loc plus 1. And we've inserted 15 into our array. It's still sorted. Happy day. We've got a sorted thing, and we've added one more item into our array. So now to do this, we could sort a array that's initially unsorted. We consider the array is broken into two pieces. Part of it is sorted, and the rest of it is unsorted. The left-hand side is sorted, the right-hand side is unsorted. If we start with the left-hand side of being sorted and we start the first one, since there's only one item in the array, it's sorted. It's in the right order. It's where it belongs. So, sort, we have an int to keep tracks of how many items we have sorted, what portion of the array is sorted. So we say sorted starts at 1 because the position 0 is already sorted. We go from 1 to length minus 1. So we're going to sort the rest of the array. So we're going to build up the array as being sorted. And then we have a for loop that does it. So then we say the temporary value of the thing we're going to insert is the value at sorted. And then loc is 1 less than that position. And then we have a while loop that is exactly the same as our insertion. So while loc is greater than or equal to 1 and the value at loc is greater than temp, we have to shift. So we do the shift, and then we decrement loc, and then when we're done with that, we've got a gap, and then we insert the temp into that gap. So let's see what this does. So we start off, conceptually temp is equal to the thing it's sorted, which is 1. So we move it into temp. Conceptually, you now have space here at 35. We can now shift 35 if we have to. Is 35 greater than 17? The answer is yes, so we do a shift. Now, our loc is 0. We decrement loc, so loc is minus 1. So we end the while loop. So we say loc plus 1 equals temp. So we insert 17. We're done with this. So we go back to the for loop, and we make sorted, or we make we grab temp, which is 11. Loc equals sorted minus 1, so it's at 1. We have our space. Is 35 greater than 11? Yes, so we shift. And then we move over. Is 17 greater than 11? Yes, so we shift. We're done with the loop because loc fell off the end. We then insert 11 into the space. And then we're done with that, so we go up to the for loop, and now sorted is now 3. And loc is 2. We move 3 over. We keep going. Make the space. 11 is not greater than 15, so we're done. We do the swap. And then we keep going until we finally get all the way to the end, and everything will be in its right place, and we have our sorted array. So we can do the insertion sort by starting at 1 and going all the way to the end, inserting that value into the right place of the sorted array to the left. Because we pull that out, we get a gap, we can do insertion. That is the insertion sort. So we start with 1, considering the thing in 0 is sorted, and then we say, where does the thing at 1 belong in the sorted piece? Keep going until we get to the end, and we'll have a sorted array. Another kind of sort is to find the largest item in the list and move it to the end, and then repeat with a shorter list. So we're going to start by sorting the largest things to the right, and actually the sorted list will be to the right, moving to the left until the smallest item is put into the left, most into the 0th element. So we do a selection sort. This is very much like doing cards. Pick the largest one, put it here, then pick the next largest one, put it next, and keep going. So we loop from length -1, which is the last position, and we go until last is greater than 0 because we want to stop there, and then we decrement. So we're going to go from right to left. We keep track of the maximum value we've seen, and then we look at 1, and max starts at 0, so we're going to claim that's the maximum 1. And then we say if they are, we keep track of which is the index of the largest value in the array. Once we've found the index of the largest value in the array, we do a swap, and that's the int temp equals max, max equals last, last equals temp. So last is going to point to the one that we're swapping to, and max is going to point to the largest one in the array. So let's see how that works. So we initialize j to 1. So now is 11 greater than 35? Nope. Is 15? Nope. 13? Nope. 14? Nope. 7? Nope. 45? Yes. 45 is greater than 35, so we want to move max. And then j is getting to last, so is 12 greater than 45? No. So the max is still 45. Last is there. So we're done with our loop. So now we want to do the swap. And now that last one is the largest value in the array, so that part is sorted. So now we go back up to the for loop, the outer for loop. So now last is 1 less, max is 0, j is 1, and then we say 35, nope, 11, nope, 15, nope, 13, nope, 17, nope, 12, nope. So max is 35. We're done with our loop, so we do the swap, and then we can go again. So we're going to keep doing this again and again and again, always finding the largest item in the rest of the unsorted array, swap it with the last, and then eventually we'll have sorted the array. And that is the selection sort. So we select the largest item and make sure it goes to the rightmost of the unsorted array. And eventually we'll have a very short array, and we'll have a completely sorted array. So we've been talking about less than and greater than, and we've been using ints. Now here we can do it in ints. All our arrays have been ints. You could do it with doubles, you can do it with floats, you can do it with longs, but these are all primitive types, so we can use the less than and greater than sign. But how do we compare strings? Because we might want to be able to do this with strings or other objects, and other objects could use the same way. We can't use the less than or greater than symbol because that is not defined for strings or player or phone entries or players or any of these other objects. So we need to use some other mechanism to determine the order of strings. So we must have another way of determining, is this string greater than this string, or is this string less than this string? So strings have a method that is actually part of an interface called comparable that returns an int. So strings have a method called compare_to that takes a string and will return less than 0, an integer less than 0, if this string is less than s, because we're going to call it on an instance of string. So if this is less than s, compare_to will return a negative integer. It will return 0 if this is equal to s, as in each of the characters are the same. It will return a positive int if this is greater than s. So we can use the compare to method to determine whether or not a string is greater than or less than or equal to another string. We can say first string dot compare to second string and then check the return value. And we could imagine doing the same thing for our sort here, where instead of doing the if a sub j is greater than, we would calculate if a was an array of strings, you would say a sub j dot compare to a sub max is greater than 0. That means the first one's greater than the second one. So you can do the same thing here with strings using the compare to method and looking at the result of the method call. If it's less than 0, then the first string is less than s, or this is less than s. If it's equal to 0, this is equal to s, and if it's greater than 0, then this is greater than s. So we can order our strings by using the compare to method that's defined on strings. You can create your own classes that implement the comparable interface. If you then you will have to implement the compare to, and you'll have to decide how do you determine greater than or less than for your object. Maybe you do it based, is a phone entry based upon their name? Is the phone entry based upon their name and phone number? Is it based upon just their phone number? It's up to you if you want to implement this compare to method. And that's this quick overview of searching, where you can do a linear search or you can do a binary search on a sorted array. And then I've given you 2 examples of how to do sorting using the insertion sort, where we create a gap and put the thing in the right place, or the selection sort, where we choose the largest and move it into the right place and then consider the largest of the rest of the array. Thank you very much for your time.